Hello, my name is Nadine Joseph. My faculty mentor is Dr. Ben Gao. Today we'll be discussing destabilizing nanosized biochar. So what is biochar? Biochar is an organic material derived from biomass such as manure, feedstock, and agricultural waste, and it goes through a process called pyrolysis, which basically enhances its surface area, deepens its pore structure, make it have a higher stability and enrich functional groups. And based on these characteristics, it could go to different fields such as biofuels or the wastewater treatment industry. Specifically in the wastewater, it is categorized as a potential absorbent as it is able to remove both organic and inorganic contaminants from a solution. Why biochar? The removal of organic and inorganic contaminants from wastewater has been a challenge, as with different types of waste may require different methods to treat them. And absorbents like activated carbon have been widely used in the wastewater treatment industry as it has been able to remove both organic and inorganic contaminants at an effective rate. The problem is that its cost has impeded its use, which is why biochar is being offered as a cheaper alternative. Of course, treatment of wastewater is imperative to protect the environment as it would prevent catastrophes like this to occur. What is ball mill biochar? Well, ball mill biochar is what basically nanosizes biochar. So if you have an unmilled sample of 2 micrometers, you could mill it to 200 micrometers. So basically this enhances biochar's absorption abilities by increasing both the external and internal surface area, which then exposes surface functional groups onto biochar's surface. The cons to that is because the particles are so fine, it has now an increased stability and suspension in aqueous solution, meaning that it's harder to separate it from the solution itself, thus preventing aggregation. So the purpose of the study is to use conventional coagulation and flocculation methods to destabilize ball mill biochar from aqueous solutions in order to enhance its compatibility to the current wastewater treatment. So what we want to do is basically turn this water into this, which is where the particles are aggregated at the bottom of the jar. So this is the general coagulation and flocculation process. So you have negatively charged particles in a solution. You'd add a positively charged chemical to it, which would neutralize these particles. And flocculation happens when these particles actually stick together. Sedimentation is what we're looking for, which is the aggregation of the particles at the bottom of the jar. For our methods, we'll be using aluminum sulfate hydrate as a coagulant, testing this with 2 different type of biochars, bagasse and bamboo, and at different pH of 4, 7, and 9. This is to investigate the effect of pH on coagulation. And once the optimal pH and coagulant dosage is determined, we'll be using chitosan as a coagulant aid to see how it would react with aluminum sulfate. And next, the coagulation flocculation mixing sedimentation period. So mixing is general 25 minutes for coagulation and flocculation to occur, and the sedimentation is what we'll be collecting our samples from, and that's for 30 minutes. So results at a pH of 4. As you can see, there's not much of a difference or improvement. The percent removal is less than 30%, so it doesn't change much. At a pH of 7, there is a much higher improvement here. As you could see, there's nearly a 100% removal, and our optimal dosage on both samples is actually 20 milligrams per liter because it has a low dosage with a high percent removal. As you can see, when you increase the dosage of aluminum sulfate from 30 to 60 milligrams per liter, there's an insignificant change. So 20 is best here. At a pH of 9, it's different for both samples. For example, bagasse biochar, as you increase the dosage, there's an increase in the removal percentage of biochar. But with bamboo, as you increase the dosage, there's not much of a change occurring. So this suggests that the type of material or sample used may play a role in the destabilization process. So for future work, I'll be using chitosan to test its effect on destabilizing nanosized biochar, and the dosage will be from 0.1 to 60 milligrams per liter. Our general conclusion is that the coagulation process works for destabilizing nanosized biochar pH of 7, and a dosage of 20 to 30 milligrams per liter are the optimal conditions. And nanosized biochar produced from different feedstocks will have a similar destabilizing performance. These are my references, and